Back in the first semester, I lectured on the vector cross product. When I did so without unit vectors. When you do include unit vectors in the description of the vectors themselves, then there's a little bit more to the vector cross product than what we've already gone through. The easiest way to illustrate is to just take a look at two example problems. Okay, part A of the example problem that we'll look at is relatively straightforward, but we begin to see the difficulties or the complexities involved in unit vectors when we eventually get to part B of the problem. But for now, let's take a look at part A. Okay, so find C is equal to A cross B for the following. Go ahead and copy the problem down into your notes, please, if you haven't already done so. Okay, so in part A of this example, we have the following. Okay, vector A is 3i hat plus 4j hat. Vector B is 6i hat minus 2j hat. Okay, now of course the vector cross product does obey the right-hand rule, but the magnitude of vector C, remember, is the following. Vector C is equal to AB sine theta. That is in terms of its magnitude. So we need three things here. We need, first of all, the magnitude of each vector. That's easy to find, just a little bit of Pythagorean theorem. Vector A has a magnitude of 5. It's just a 3, 4, 5 right triangle. Okay, and then vector B, let's see, 36 plus 4, and then take the square root of all of that when you do the squaring here. And you end up with vector B as being a magnitude of 6.3. But then, of course, we need the angle between the two vectors. So let me go ahead and draw out here the xy plane. Like so. Okay, and then vector A is into the first quadrant, so over 3 and up 4, it roughly looks something like this. And then vector B, you'll notice here, is into the fourth quadrant. It's over 6 and down 2. It's something like this. So then therefore the angle theta that we need, like so, is this angle here. So I'm going to do a little bit of basic trig here to find the angle that each vector makes with respect to the x-axis. Then I'll just add those angles together to get this green angle theta. So let's go ahead and find this red angle here, like so, associated with vector A. That's just going to be the inverse tangent of opposite over adjacent, so inverse tangent of 4/3. Okay, so that's about a 53-degree angle right here. Okay, and then we'll do the same thing here with vector B. We'll find that red angle there. We'll ignore negative signs. So that's going to be the inverse tangent of 2/6. So inverse tangent of 2/6. And that comes out to be about 18 degrees roughly, like so. And then, of course, add the two together then to get the angle theta. So 53 plus 18 is 71. Okay, so now I've got everything I need. Now I can go ahead and calculate the magnitude of C. So I've got, first of all, A, 5, times B, 6.3, times then the sine here of 71 degrees. And that then ultimately gives me about 29.8 or so, give or take. Like so. Okay, and then in order to get the direction of the vector C, we then do A cross B. So A cross B looks like this using right-hand rule. Therefore, on this two-dimensional diagram, C here is into the board. The question is, however, is that the positive Z direction or is it the negative Z direction? Well, this is where the ambiguity starts to come into play here associated with the unit vectors that were given in this problem thus far. There is a way to resolve, however, this difficulty. I'll get to that in just a few moments. But for now, let's go ahead and take a look at a three-dimensional picture of this problem. Okay, so here's X, and here's Y, and here's Z, like so. And then in the XY plane, we first of all have the vector A in the first quadrant. In other words, it's a positive X component and a positive Y component. Vector A in the first quadrant in the XY plane looks something like this. But then vector B is a positive X component and a negative Y component. So let's see. This gives us an idea of the three dimensions of the diagram. So then therefore for vector B, which is a positive X component like so and a negative Y component, it looks like this back here. Like so. It's in this quadrant in 2 dimensions here on this diagram in the XY plane. So then therefore in the XY plane, the angle theta that we indicated earlier is actually this angle right here. So then therefore, using right-hand rule, watch this, if you do A cross B like so, that then gives you the vector C downwards on the diagram in the negative Z direction. That would be negative K hat in terms of a unit vector. So then therefore, I'll draw it here in red, like so, pointing straight downwards on this diagram is the vector C. So then therefore I would have to write vector C as negative 29.8 k hat, like so. Okay, notice that I was able to complete this problem and do so correctly, but I had to kind of futz around with it a little bit here in terms of the basic trig. I had to do some trig to find magnitudes of the vectors, figure out exactly what the angle was there in green on that two-dimensional diagram, and then switch here to 3 dimensions to correctly get the direction of the vector C. Watch how this difficulty compounds itself, that instead of being given two two-dimensional vectors in the xy plane, let's say that instead we're given two three-dimensional vectors. So there's a part B to this problem. Okay, so in part B of this example, here's then what we're given. We're given that A is negative 2i hat plus 4j hat, but then minus 3k hat, like so. And then vector B is given to us as 6i hat plus 3j hat, and then minus 5k hat, like so. How do we find the cross product of these two three-dimensional vectors? We would have to find their magnitudes, which involves three-dimensional Pythagorean theorem, but we would also have to find the angle that is formed between those two vectors. And then we would end up with another three-dimensional vector, and we would have to correctly write down the x, y, and z components. That's difficult to do based upon what we've already seen for the vector cross product. But as I said at the beginning of this lecture, there's a little bit more to the vector cross product than what we've already gone through. Here's the easiest way to illustrate. Let's forget about this for now. Let's say that I just have generically two three-dimensional vectors. So here's vector A sub x I hat plus a sub y j hat plus a sub z k hat. Okay, here's vector B sub x I hat plus b sub y j hat plus b sub z k hat, like so. So two three-dimensional vectors. Okay, let's go ahead and find the cross product. Let's go ahead and do C is equal to A cross B. Okay, so then therefore I'm going to have the following. A sub x I hat plus a sub y j hat plus a sub z k hat cross b sub x I hat plus b sub y j hat plus b sub z k hat. And now let's just FOIL all of this out and let's see what happens as I do. Okay, now the first term of my foiling process here is going to be this quantity here multiplied by this quantity here. However, I'm going to write it like this. Watch this. Like so. Okay, and then I've got this term here multiplied by this term. Okay, here's how I'm going to write that. Like so. So take a look at that carefully. Okay, and then this term multiplied by this term. Like so. Okay, and then I got the next three terms. So the next three terms, the first one is going to be this times this. Like so. Okay, and then this times this. Like so. Okay, and then the last of the middle terms is going to be this times this. So, okay, and then the last three terms, the first of which is going to be this times this. Like so. Then this times this. Like so. And then lastly, this times this. Like so. And then if you look at this carefully, out of this huge mess that I've obtained in this foiling process, I end up with 9 cross products. 1, 2, 3, and so on. Cross products between the individual unit vectors. Okay, let's look at those cross products a little bit more carefully. In order to examine these cross products more carefully, let's draw out the unit vectors. Actually, let me give myself here one more layer of board to work with. Okay, so right here, coming straight out at us is I hat in the x direction. Perpendicular to that, like so, is j hat in the y direction. And then perpendicular to those two, like so, in this direction, the positive z direction, this is k hat, like so. All three of these vectors are are perpendicular to each other. Okay, so let's take a look at these individual cross products. Let's first of all take a look at I cross I. In other words, what we're doing is we're taking the cross product between a vector and itself. What is the angle between a vector and itself? It's 0, and the sign of 0 from the magnitude of the cross product is equal to 0. So I cross I is equal to 0. J cross J is equal to 0 for the same reason. And K cross K is equal to 0, like so. So immediately those three cross products drop out. Okay, now let's take a look at this cross product right here, I cross J. What is that equal to? Well, you take the magnitude, first of all, of the first vector, which is 1, multiply that then by the magnitude of the second vector, which is 1, and then multiply that by the sine of the angle between the two vectors. Okay, the angle between I hat and J hat is 90 degrees, sine of 90 degrees is equal to 1. So then therefore the magnitude of the unit vector that you end up with is equal to 1, but which unit vector is it? Watch this, and then also take a look at this diagram here behind me. I hat cross J hat is K hat, like so. Okay, next in these cross products, let's actually take a look at this one here, J cross K. Once again, take a look at the diagram behind me. The magnitude of the vector that we'll end up with is once again 1, but it's specifically a unit vector. Which unit vector is it? Well, J cross K is the following. Watch this and look at the diagram here. J cross K is I hat. Like so. And then the next one that we'll take a look at is this guy right here, K cross I. Once again, this is going to give us another unit vector, but which one is it? Take a look at this diagram and then watch this. K cross I is J, like so. So K cross I is J hat. What you're seeing here is actually what is called a cyclic permutation. And this cyclic permutation follows the letters I, J, K alphabetically. So for example, I started with this right here. I cross J is equal to K. And then the next permutation in this cyclic permutation is J cross K, which is the next letter I. And then after that, the final one in this cyclic permutation is this quantity right here, which is K cross I, and then you get the next letter J, like so. But then, of course, we could also go backwards with the letters. Those are the other three cross products that remain. So, for example, let's take a look at this cross product right up here, I cross J. Watch this, or I cross K, excuse me. Watch this carefully. So first of all, we have I hat like so, cross K hat. That then gives me negative J hat. So this guy right here is negative J hat. Okay, watch the others. They will also give us negative unit vectors. So for example, this one right here, J cross I. So watch this carefully. J cross I is negative K, like so. So this guy right here is negative K hat. And then the last one of this cyclic permutation of the letters going backwards is K cross J. You could probably guess that this is negative I, but here's then how you show that. Watch this. K cross J is negative I. Like so. Once again, these are examples of what are called cyclic permutations. I, J, K, K, J, I, giving you negative values in that second case. Okay, now after I've done all of these cross products, then what do I have left over? Well, here's what I have left. Okay, let's group all the terms together. So first of all, you're going to notice here that there are two groups of I hats, if you will. So the first value of the I hats, the positive one, is this guy over here. So I have a sub y times b sub z. That's going to be a positive I hat. But then I also have this guy right here, which is in terms of a negative I hat. So this is going to be an a sub z times b sub y. Like so. And now I've gotten rid of all of the I hat terms. Okay, let's do the same thing with the j hat terms. So we have, first of all, a positive j hat quantity. That's this guy right here. So a z bx. Like so. But then we also have, let's see, where is it? Right up here, a negative j quantity. So I'm going to have a minus ax bz. Like so. And then lastly, we also have k hats, of course. There's a positive value. Let's see, where is it? Here it is. So here's the positive value of k hat. So ax by. And then lastly is our negative k hat, which is this guy right here. That's ay bx. Like so. So after we do the cross products and after we group all of the terms together, you end up with this expression right here. Take a look at this expression carefully. You've seen an expression like this before in math class. It's describing what? It's describing the determinant of a 3 by 3 matrix. So here's how we would write that determinant for this case. First row of the matrix are the unit vectors, I hat, j hat, and k hat, like so. And then the second row is a sub x, a sub y, a sub z. And the third row is b sub x, b sub y, b sub z, like so. So recall how you calculate the determinant of a 3 by 3 matrix. The first term is AYBZ minus AZBY, all times I hat. That's this guy right here. And that's usually the middle term that kind of switches everybody up. It kind of depends upon which math teacher you have or which textbook you have when you first learn how to calculate the determinant of the 3 by 3 matrix. Sometimes this negative sign is pulled out to the front like so and the terms are reversed. Quite frankly, I don't like to do that because it just confuses me. So instead what I do is I say, okay, for the j hat, which is the middle term, then we're going to have azbx minus axbz, like so. And that's exactly what we have. And then the last term, the k hat, is easy. For the k hat, it's axby minus aybx. That's this guy right here. So however you're comfortable in remembering how to deal with the middle term, that's perfectly fine. That's up to you. Okay, so let's now go ahead and apply this determinant here of the 3 by 3 matrix to the two problems that we had. So let's actually jump back to part A of the example. Let's do that first. Let's use this determinant here, and then we'll do it for part B of the example as well, which is the problem we haven't yet completed. All right, so let's jump back to part A. Okay, so recall what part A was. So we had 3i hat plus 4j hat, and then B was 6i hat minus 2j hat. Remember the ambiguity that we had in determining the direction of the vector C? We found that it was in the negative k hat direction. Okay, let's go ahead and illustrate that here by now writing this as a determinant. So C is going to be the determinant of the following I, j, k of 3, 4, 0, and then 6, negative 2, 0, like so, when I fill in my vectors. And then let's go ahead and then determine the determinant here of this 3 by 3 matrix. Let me give myself some room here to do so. Okay, so the vector C is going to be, first of all, 4 times 0 minus 0 times negative 2, all I hat, which is 0. Okay, and then we have the j hat term, which is going to be 0 times negative 6 minus 3 times 0, which is still 0. And then lastly, we have the k hat term. So the k hat term is going to be 3 times negative 2 minus then 4 times 6 all times k hat. And now let's go ahead and simplify. Negative 6 minus 24 is negative 30. Negative 30 k hat, like so, which was the answer that we obtained earlier. I didn't round it off, however, in part A. Now let's do the same thing for the more difficult problem, which we haven't done yet, which is B. Once again, let's give ourselves some room here. Okay, so now here's B. Let's go ahead and get back to that. Let me rewrite it here. So vector A is negative 2i hat plus 4j hat, and then minus 3k hat. Vector B is 6i hat plus 3j hat minus 5k hat, like so. And now let's go ahead and find the vector C. Okay, so determinant of the following. Okay, I, j, k, and then we have negative 2, 4, negative 3 for the vector A, 6, 3, negative 5, like so for the vector B, okay? Okay, and now let's see what we get. Okay, I'm going to use some brackets here. Okay, so first of all, for I hat, we're going to have 4 times negative 5 minus negative 3 times 3. Got to watch your negative signs, of course, when doing all of this. This is all I hat. Okay, and then we've got the j hat term. So negative 3 times 6, like so. And then minus negative 2 times negative 5. That's going to be j hat. Once again, we've got to watch our negative signs here. Okay, and then lastly k hat. So negative 2 times 3 minus 4 times 6. Like so, and now we go ahead and simplify. All right, so after all of that, vector C is as follows. Let's see, this is negative 20 minus negative 9. So negative 20 plus 9 is negative 11 I hat, like so. Negative 18 and then minus 10. So be careful once again with all the negative signs. So negative 18 minus 10 is negative 28. That's j hat. And then lastly, negative 6 minus 30, so negative 36 k hat, like so. So ultimately, the vector cross product is the determinant of a 3 by 3 matrix.